The primary focus of this lesson will be on the punched intercept spacer. Here we will inspect the raw material per the standards outlined in GED document ED-0019, Intercept Spacer Frame Raw Material Specs, and the flat punch strip as it comes out of the feeder press per the standards in GED document ES-0008, Intercept Spacer Finish Spacer Specs.
ED-0019 covers raw material specifications for all types of intercept spacer materials. This includes ThinPlate, ThinPlate, and ultra stainless, as well as Blackline versions of each of these material types. Depending on the construction of an intercept machine, it may be configured to run either ThinPlate spacer or ThinPlate spacer and ultra stainless steel spacer. Earlier intercept models were originally designed to run ThinPlate material, which is a thicker spacer material measuring approximately 10.5 thousandths in thickness. Some of these machines have been converted to run thinner ThinPlate and ultra materials, which is approximately 8 thousandths in thickness. These thinner materials, especially the ultra stainless steel, provide better warm edge performance than the ThinPlate spacer. All current intercept production models are designed to run these premium warm edge materials. Quality checks that should be made on the raw spacer material are the material thickness and slit width. Looking at the material description in ED-0019, the material thickness for Intercept Ultra Spacer should be 76 10,000ths plus 8 10,000ths to -0. The slit width should be the nominal material width for a particular spacer size plus 0 to -5 thousandths. The maximum burr allowance on the slit edge is 10% of the material thickness, which for this material would be 7.6 10,000ths of an inch. This is less than a 1,000ths burr. A burred edge results from dull slitter cutters and is an issue to be discussed with your material supplier. Looking at the material description for ThinPlate steel, the material thickness should be 77 10,000ths of an inch, with an acceptable range of 69 10,000ths to 85 10,000ths. The slit width is also plus 0 to -5 thousandths tolerance, but with no burr. The edge is to be burr-free. Refer to ED-0019 for additional raw material specs for other spacer material types like this one for ThinPlate Blackline spacer material. When you have completed this series of videos, you will be directed to the operations series for your particular model of the Intercept Spacer Frame machine. That series will provide detailed setup and operations instructions for your machine, including a discussion of quality checks that the operator should perform prior to running the machine. These checks verify that the machine is properly set up. These checks include checking the parting width to verify the feeder press width is properly adjusted, checking the finish spacer width to verify the roll former width is set correctly, and checking the tab or leading edge width to verify the cutoff width is set correctly, swaging the tab so it is 25 thousandths to 35 thousandths smaller than the measured spacer width. Measuring the parting material width is a quick check to verify the punch depths of the tab or leading edge dies. It assumes that if the tab dies are punched at the proper depth, that all other punches are within spec as well. Document ES-0008 provides the punch details for the two standard profile tab types, Standard Tab and Corner Plus Tab. A standard tab includes the first corner. Therefore, the punch depth of the parting area also affects the punch depth of the first corner. The Corner Plus tab die separates the two, so adjusting the parting punch depth does not affect the corner punch depth. All corner punches are made with the corner dies. The parting width is derived by taking the nominal material strip width for a particular spacer size and subtracting the nominal tab punch depth of both sides. See the material width table in the user guide for a list of the parting widths. Verify that the measured parting width is within plus or minus 10 thousandths of the nominal parting width dimension. ES-0008 includes drawings for the two typical machine configurations, which are for standard profile with standard tab and standard profile with corner plus tab. Choose the drawing that pertains to your machine's setup. The page with the details of drawing 1-30496 illustrates the punched strip and enlarged details of each punch on a punched strip for standard profile spacer with a corner plus tab. Detail number 1 shows the corner plus tab. The depth of the punch at the parting area is 338 thousandths of an inch. The tab is also referred to as the leading edge of the spacer. Note this dimension is marked with an asterisk, as are those for details number 2 and 3. At the bottom of the page it states, theoretical dimensions are marked with an asterisk. Actual setup dimensions may vary to maintain finished spacer specification. Drawing 1-30496 states that the tolerance for 3 decimal places has a plus or minus 5 thousandths range. The theoretical dimensions may exceed these tolerances to maintain overall form of the spacer frame. One of the advantages of the corner plus tab is that the punch depth may be adjusted without affecting the first corner, as is the case with the standard tab. By adjusting the depth of this punch, you affect the height of the sides of the tab. This controls the gap on the back of the spacer where the two ends come together. Minimizing this gap improves the MVT at the fourth corner. MVT stands for Moisture Vapor Transmittance. The MVT rate is a measure of the passage of water vapor through the seals of an IG unit. A good MVT not only helps keep moisture out of the IG unit, but it also improves gas retention, keeping argon or krypton gas inside the unit. As the tab is inserted, the bottom sealant should push into this gap, becoming part of the seal in MVT path. A tighter fourth corner also improves the appearance of the inserted corner, provided it is not too tight, causing flare issues. If the punch is too shallow, the tab sides will be too tall, making it difficult to insert the tab into the end of the spacer, which could cause flaring at the assembled corner. Also, this affects the setup to the top lip at the trailing end of the punch, as shown here. If your machine has a mechanical crimper, the top roll may engage at this point if the step is too high, resulting from a deep punch depth, rather than rolling over and dropping into the first corner. This will cause the crimper to engage and crimp the tab, which is then often crushed in the cut-off swage dies. Detail number 2 shows the corner punch dimensions. The reference punch depth here is 222 thousandths plus or minus 5 thousandths. Again with the asterisk, it is a theoretical dimension. Again, it may be necessary to deviate slightly from this value in order to get the corners to fold correctly. This may be because of the form of the spacer and how the corners wrap into the bottom of the spacer. It may also have something to do with the type of material being formed. When running ultra stainless steel spacer material, it is necessary to evaluate the corners with the GED Fold Force Gauge and Excel spreadsheet to help ensure proper formation of the corner punch and to extend the life of the dies. Refer to the user's guide for details in how to use and evaluate the corner punches, or check with GED for the video on this topic. Measure the force required to fold each corner of the ultra spacers and enter this data into the spreadsheet. In this example, we have a minimum force to fold the corners between 40 and 60, a maximum over 60, and a range less than 7. The corner pre-charge was set to 30 psi. Use tables 2 and 3 and the pre-charge table to see if the spacer readings are within acceptable range. The calculation field boxes are conditionally formatted to the different range parameters. If there are any issues with these readings, click the Troubleshooting tab at the bottom left of the screen and find a similar scenario on the Troubleshooting worksheet to further evaluate the spacer condition and possible solutions. The table will offer suggestions on how to correct the issue, improving the corner quality and extending the life of the corner dies. The fold force should be checked at least daily. Detail number 3 shows the dimensions for the Muntin punch. The Muntin punch should be 48 thousandths deep from the edge of the material. It too is a theoretical punch depth with a plus or minus 5 thousandths tolerance. Typically, these are intentionally set a couple thousandths under the nominal value so the Muntin clips fit tighter and don't rattle when the window is opened or closed. Setting the Muntin punch too shallow, however, could cause the clip to spread the top of the spacer open, causing a flare issue. Flare should not exceed 5 thousandths per side. This will reduce the sealant thickness between the spacer and the glass when pressed out at the oven, possibly compromising the seal integrity. For example, if you're producing IG units with the minimum wet-out thickness of 15 thousandths and there is 5 thousandths flare on one side, then that side seal now only has a sealant thickness of 10 thousandths between the glass and the spacer. This could compromise the seal integrity and result in a premature IG unit failure.
Thank you for participating in this lesson on punched intercept spacer quality checks. Please continue with the next lesson on formed intercept spacer quality checks. When you have completed the 3 lessons in this finished spacer quality check section, please continue the course on intercept spacer folding techniques.